Okay, let's get started. I sent out an email today regarding dry labs versus wet labs. And some of you had some questions about that. Whenever you see dry lab, it is a worksheet basically. I'm going to be in here doing it. And it's long, really long, but it's a worksheet. And I'm going to publish the answers as well, depending on how my back is. I could not walk yesterday. Oh, I've never had my back go out. It's my lower back. Oh, I took two pain kills and it helped. It didn't go away. It was like, what the heck did I do? Okay, so anyway, and today we're having a dry lab, continuing from yesterday. Now, so what you're gonna be doing in a dry lab is just filling out your lab manuals worksheet on nomenclature. Now, in this school, the nomenclature is a big deal. Some schools, it just depends on what school you're taking 1A at. This school, it's a big deal. That's why they're devoting a whole bunch of time to it. Hence, I'm going to be devoting a lot of time on your test next week to naming. And on your test, again, you have a 3x5 card if you like, both sides. Your phone have to be turned off. If you're using a TI 83, 84, 89 calculator, you need to show me you've cleared memory. Okay, now we're having 3 wet labs in a row. Okay, there's one tomorrow on hydrates. The next one's on net ionic equations, and that's 2 days. It's a 2-day wet lab. And then there's another one on heats of formation after that. So, and again, those are due 1 week after the day you do them. So on the next, not tomorrow's lab, but Thursday's lab goes from Thursday to Monday. So we do a week from Monday, the last day of the lab. Okay. And some of you are asking questions about the quiz. The class in general did really well on the quiz, really well. So I'm really happy about that. The only question was the last question, and it was a sig-fig question. So let me just explain really fast. Whenever you are using displacement to determine volume, which that problem was, you're going to do a delta volume change. That means you have to subtract. When you subtract, you ended up with a 3 sig fig number, not a 4. And that's why the answer was in 3 sig figs. Okay. And if this was a real test, I would give you partial credit if you put the other one down. But because it was multiple choice, it's either right or wrong. But in general, you guys did really well. I'm very pleased with that. Okay, let's see. Oh yeah, I need to give you my opinion about our school and their reflection on Juneteenth Day. Every school that I know of had yesterday off. If you look up the federal holiday, if you look up what a federal holiday is, you're supposed to be public places have that off. We're a public institution. We should have had it off. That's why I told you guys, you know, if I wanted to do a video. So you guys, if you wanted to participate in an activity, at least it wasn't my class keeping you from doing it. Okay, so, and this is the second year. It's not like the first year. Usually the first year they give you some like leeway, kind of a grace period to implement it. But I don't know what to say about our school. But anyway, I'm very disappointed that our school did not recognize that. So, okay, what I'm gonna do is I'm gonna continue on and talk a little bit more about naming binary compounds, particularly the ionic compounds. And if you haven't started on that worksheet yet, there's a lot to it. Now we're gonna be here till everyone's done. And when I say everyone done, that's whatever your feeling is. Like if you want to do part of it here and part of it at home, that's fine with me. It's just that I want to make sure I'm here to answer any questions. Okay. All right. So I'm going to continue off from the video I did last time here, from this slide here. Okay. So there are 2 kinds of compounds, ionic and covalent. Ionic compounds require a cation and an anion, no exceptions. The reason for that is an ionic compound transfers an electron. So if we have sodium and chlorine, when those combine together to become more stable, an electron from the sodium is going to be donated to the recipient chlorine. So this now becomes an ionic compound. There's two ways to look at ionic compounds. The first is see if the first part is a cation. If it is, then check to see if the second part is an anion. If it is, it qualifies. Or metal plus nonmetal. Now the periodic table is mostly made up of metals. All the red in there is, all the red there are metals. So most of the periodic table are metals. That means most of the periodic table is going to be a cation if it forms an ionic compound. There are much less non-metals, and these form anions. So if you're up in the air as to, well, should I treat this ionically or should I treat it covalently? Just look at the first element. Is it a metal? If yes, look at the second one. Is it a non-metal? Those are ionic compounds. Now, ionic compounds have to have, no exceptions, have to have a net charge of 0. That means the charge on the cation has to be equal to the charge on the anion. No exceptions. So this is +6. This has got to be -6. +3, -3. Okay. Absolutely net charge of 0. There are no isolated charges in the universe. That's extremely unstable. Instability, of course, rules the universe. Okay. So when you're determining how many sodiums you need, how many chlorines you need, you're looking at charge neutrality. So if we have something like barium hydroxide, how would you write the formula for barium hydroxide? Well, first of all, is this ionic or is it covalent? Well, barium is a metal. Hydroxide is an anion. The charge on barium is +2. Charge on hydroxy is -1. So this is the hydroxide ion. Barium is +2. So those are not balanced. So we have to have 2 OHs to get us up to -2, so that's a net charge of 0. So the formula for barium hydroxide is that. Now you should be able to go from the name to the formula, formula to the name. And there's a whole bunch of practice on your lab, dry lab. Okay, is this clear? That it has to be, there are no exceptions, has to be net 0. Now the tricky part comes into sometimes when you're working with like aluminum sulfate. Okay, this is ionic because aluminum's a metal, sulfate's an anion. So the charge on aluminum is +3. Sulfate is -2. Okay, so that is not charge neutral. So we've got to modify the numbers of the aluminum and the numbers of the sulfate so we net 0. Now, one way to think of it is, what is the common denominator between 3 and 2? 6, right. So how many 3s are in 6? How many 2s in 6? And frequently it's 6. So that's the formula for aluminum sulfate. Now, on Canvas, I have a chart. Yeah. Usually, yeah. Yeah, because when you face a situation where you're trying to, you have an odd number and an even number, and you have to, like when you, if you're going to add 1/2 plus 1/3, you can't add it directly. You got to have a common denominator, right? And it's usually 2 and a 3, so it's a 6. So how many 2s are in 6? How many 3s are in 6? The rationalization. Yeah, frequently. I'm not sure I've ever. I'm going to say frequently, not all the time. I can't think of any good examples though where it's not 2 and 3. Okay. So if you haven't printed off this ion chart, this would be really helpful. I'm going to give you this next week on your tests. Now, if you're taking this class from another professor, sometimes they make you memorize a whole bunch of ions. And everyone's got a cell phone, right? And why memorize something when you can look it up in seconds on your cell phone? But for the test, you can't use your cell phone. So I'm going to give you the chart. But so anyway, download this and have a printout of it. Also handy to have at the same time a periodic table. So there's one online, there's one in your lab book. Yeah. Yeah, when I say lab book, yeah, packet. Okay, now I want to call to your attention, and this is something that a lot of professors do not teach, and I'm confused why. I'm talking about it at Sac City, Sierra, Tacoma, South Puget Sound, Green, all those community colleges I've taught at, they don't teach 2 ways of naming cations. There's the old way and the official way. The problem is the world still uses the old world naming. So let's look at chromium. Now, if you name this chromium 2 sulfate, for example, so we're looking at, let me just write this over here. Now, the problem with trying to name chromium sulfate, okay, this is a metal. The problem is the metal is in 2 ionic forms, a +2 and a +3. So you need to differentiate which one you're using if you're writing this out. Now, this is the way, if you're in a chemistry class, this is the way you write chromium +2, chromium +3 with a Roman numeral here that designates the charge. However, if you are in an agricultural environment, a food environment, drug environment, you don't see chromium 2, you see chromous or chromic. And you need to know that there are 2 names for Cr +2. Now I've listed the ones that are very common. And those you should be comfortable with going either way. So if I gave you the formula, CrSO4, what are the 2 ways of writing that? Well, sulfate is a -2, and there's 1 to 1, so that means what charge must the chromium be then? It's okay to, what must the charge? +2, right? Okay, that means it's a +2, that means it's chromous. So the name of this is chromous sulfate or chromium 2 sulfate. So those are the two equivalent names for that. Yeah. I'll ask you if there are two names, please list two for full credit. Okay. Now, again, a lot of schools don't want you to know this. They say, oh, they have to memorize too much. But the problem is if you look on your candy bar for the ingredients list, they're not going to say, they're not going to have chromium sulfate in it, but they're not going to say chromium 2 sulfate. Never. They'll never say that. They'll say chromous. And I want you to be aware that there are two names. I have a lab over at Sac City, and the lab chemicals on the cart was cupric sulfate. And my students all came up to me, we can't find cupric sulfate. I said, it's right there. Because it was the old world name. And their lab packet, get used to saying that, didn't say that either. So anyway, you need to be aware there are two names for some of the cations. And I listed them on here. Okay, the other thing about ions, does that make sense? Any questions about that? Yeah.
I know the second log for this part of it, they have some elements that go up to like +4. So what is the like low to high, those versus A? Like where does that?
That's a good question. She said that sometimes there are more than two, which is where you're going with this, right? There could be 5, like vanadium goes up to +5. 1, 2, 3, 4, 5. Well, the only ones they name are these two, the us and the ick. I've never seen other ones. So it's just going to, no, not necessarily. The upper one is going to be ick. The lower one will be an us.
Yeah.
But not necessarily +2 and +3. It could be. Yes. Yeah. The higher one is going to be the ick. The lower one is going to be the us. Yeah. Okay. And they're only for the cations. Yeah.
Same suffix applied for negative ions.
Yes and no. I'm going to talk about that in a second. The negative ones are a lot trickier than these. There's a whole bunch of versions with different oxygens in it, and you have to pay close attention to the name. Like nitrous, nitrite, they differ by one oxygen. Some of them differ by, there are like 5 versions of it, and the only version difference is the number of oxygens in it. Those are called polyatomic anions, and they're you just have to be careful with them. That's all. They're not tricky, other than the names. I forgot where I was going with it. Oh yeah, all the cations except for 2 are 1. There's no poly cations except for 2. One is ammonium. The NH4 plus. That's one of the polyatomic cations. Okay. This is a very common ion, like ammonium hydroxide. When you buy ammonia in a jug at the market, it's ammonium hydroxide. So it's NH4OH. The other one is mercury. Now, mercury's weird because mercury 1, what's the charge on mercury 1? Plus what? +1, but there are 2 of them. So that's why it's +2. Total, yeah. They're both stable. Otherwise, we wouldn't find them in nature. It's just the +1 charge is tied up with another one, but they're together as a group. So you treat it as the group charge. We're going to see in the anions, there's a group charge. So mercury 2 means it's +2, and there's only 1 of them. So the charge on this mercury is +1, the charge on this one's +2. But as a group, it's still is a +2. Well, there's two of them. Two of them, if two are equal to +2, that means each one's +1. And that's the only math. Yeah, exactly. Yeah. And if it's written like this, you don't have to guess because that's the charge. But again, you're not going to see this when you look at your food and stuff. You'll see these guys. That's the disadvantage of not teaching the old system, you know, and our economy tends to not want to change. You know, they've got, you know, box cars full of mercurous chloride. They don't want to name it mercury 1 chloride. They have to change all the names, and that's called overhead. They want to minimize overhead. So they stick to the old name, mercurous chloride. Same with food, particularly food. Okay, does that make sense though on the two names? And then the cations, there are only two that are common. There's some weird ones, but the two most common ones are the mercuries and then ammonium, NH4. Okay, let's look now at the anions. Anions are much more complex than cations. Now, the simple anions are these guys here. They're monoatomic. All the rest are polyatomics. Polyatomics are a group, and they're stuck together for stability reasons, but they're stuck together. Because they're stuck together, they have a group charge. You cannot consider each part of it as a separate charge and add them together. The group has got one charge. For example, in the case of phosphate, PO4, a charge of -3. Now, the thing about the anions is there's lots of polyatomics, lots of them. I mentioned earlier, nitrate versus nitrite. They're both -1, but one's got 3 and one's got 2 oxygens. So when you go buy a package of bacon, what does everyone say the bad health effects of bacon are? There's a couple things, but.
Cholesterol?
Hmm?
Cholesterol?
Cholesterol is one. What else? Sodium. And the sodium is from what chemical? You're absolutely right, but what do they quote as carcinogenic about bacon? Nitrites. Yes, because nitrites, when you cook it, forms nitrosamines. Nitrosamine is a known carcinogen. So there's uncured bacon. Has anyone seen the term uncured bacon? Uncured bacon has more nitrites in it than the ones that have nitrate added directly. That's because they add celery salt instead of nitrite. Guess what's in celery? Naturally, nitrites. That's why the bacon tastes the same. It's because the celery contains sodium nitrite. So they can say, oh, it's not a cured meat, but it is a cured meat because cured meats are cured with sodium nitrite. What that does is it binds up protein in there, forms with the myoglobin and the protein, binds it up. Okay, so back to this though. The purpose of the polyatomics, and me talking about it, is just be really, really careful about your naming. Because nitrate, as you can see here, and nitrite aren't the same. Yeah.
So what's the difference between polyatomics and like a molecule?
Well, polyatomic means more than one atom. So the anion contains, if it's a polyatomic anion, it contains more than one atom. It's a group.
That same element.
Usually it's mixed with oxygen. Like nitrogen by itself is a mono or just an atomic anion. Throw in an oxygen, throw in two oxygen, and they all, one becomes nitrite, one becomes nitrate. Throw in some cations and becomes nitric acid. I mean, so in all oxygens, because we're in an oxygen environment, frequently things are combined with oxygen. When you mine something, like you're going after uranium, you don't get uranium when you mine for uranium, you get uranium oxides. So you've got to take the oxide out. So there's a chemical process to do that. Same with sodium. You have something called slaking. What that is it means it's pulling out the oxygen. So because we're in an oxygen environment, we got a lot of combinations of oxygen. So again, I want to reiterate. Look at all these chlorines. Now the one up above, the monoatomic chlorine is this. Throw in one oxygen, it's called hypochlorite. Throw in two oxygens, chlorite, three oxygens, chlorate, four oxygens, perchlorate. So just all the different combinations with chlorine gives you different names. And it goes back to how many oxygens are tied up with the mono anion. Okay, so bottom line is their group, and the group has a charge of -1. Notice this one has a charge of -1, and this one does too. And that one, and that one. So by adding oxygens, it could change the charge, or it may not. You just have to look at it and see. Okay, that makes sense? Okay, all right. So that's the ionic naming convention. You got a balanced charge. And you fiddle with the numbers, so you have a net charge of 0. Covalent is significantly easier. Most students find covalent much easier. Covalent is going to be using the mono, di, tri, tetra numbering system, because with covalent, there's no charges involved. Now, a bond happens when two elements come together. For what reason? If in doubt, stability. Okay. The bond does not happen unless the result is more positive, period. Otherwise, from an energy stability standpoint, what's the point of forming something that's unstable? Because once you form it, guess what it'll want to do? It'll want to go back to its more stable state. Okay, so I want you to keep in mind the number 8. And we're going to elaborate on this number 8 a lot in future units. But for now, think about the letter of the number 8. People sometimes refer to it, well, actually frequently refer to it as the octet rule. Okay, so if we look at sodium chloride, remember I said when it's an ionic compound, an electron is transferred over. We talked about groupings on the periodic table. Remember? So all the groups in group 1, tend to form a +1 cation. Group 2 is +3. Group 3 is +2. Group 3 is +3. The carbon group, because it's neither +4 or -4, it doesn't form an ion. And then it goes -3, -1, -2, -1. Okay, if you look at sodium, how many electrons does sodium have for neutral sodium? Yeah, 11. And those are distributed in different orbitals. The outermost orbital, called a valence orbital, it has 1 electron. And that's a simplified Bohr orbital. It's much more complicated in this simple planetary model. But notice we go 2, 8, and whatever's left over. So the outermost orbital is called the valence orbital. So how many electrons are in sodium's valence orbital? 1. These are not valence because they're inner core electrons. Okay, inner core electrons Okay, so core electrons, the innermost electrons, are very, very stable. So these do not react because they're already stable. This guy is a valence electron and it is not stable. So plain old sodium is very reactive. If you go and get sodium metal, it's so reactive you buy it covered in oil. If you drop it in water, it immediately reacts with the water. In fact, up at Hanford in Washington State, which was part of the original Manhattan Project, they had a whole bunch of sodium metal they needed to get rid of. So they dumped it into a pond, a big pond of water. Guess what the pond of water did? It boiled because that sodium metal was so unstable, it reacted with water to form sodium hydroxide. And it boiled it. It was so intense.
That electron was just moving around with all the other atoms playing around. That's what caused it.
It wanted to get rid of that electron. And why did it want to get rid of the electron? Once it got rid of this electron, this became the valence electrons. Remember 8? 8 stable. So it wants to go to this here without that. That's why it's a +1, because it wants to get rid of it.
And what happened was that radiation.
Huh?
But what happened was radiated from this reaction.
Whenever you go from unstable to stable reaction, usually you give off heat because you're converting the potential energy to kinetic energy. And kinetic energy is manifest in a molecule as heat.
So they're turning sodium as the base of a nuclear weapon.
Oh, no, they have tons of stuff going on. It was just a byproduct of one of their deals. So that's why sodium wants to form a +1. It wants to get rid of that, become more stable. However, you cannot just get rid of an electron. You have to have a recipient. So in the case of chlorine, chlorine is a really nice recipient because it likes to form a -1 anion. So it wants electrons. Sodium wants to get rid of it, become more stable. Chlorine wants to gain one to become more stable. So let's look at chlorine now. Chlorine has how many electrons? Just plain neutral chlorine. You guys need to know this, okay? What does that number there mean? Electrons and protons, right? So neutral chlorine has 17 electrons. So the question is, okay, so that's what chlorine looks like. How many atoms, excuse me, how many electrons are in the outermost valence orbital? Well, we've got 2 here, core, 8 there, core. 8 and 2 is what? 10. And it's supposed to, a neutral chlorine is going to have how many then in the outermost orbital? 7. So the reason why chlorine likes 1 electron is why? It is an odd number, but that's not the reason it wants 1 though. Yeah, 8. Right, that's what you're going to say, right? Yeah, so the electron from the sodium is given to chlorine. So sodium is happy now. It has an octet on its outer orbital now. Chlorine is happy because it's got an octet on its outer orbital. That's why the ionic bond forms. One gives up, one receives. Now this applies except for the first one, because you only put 2 electrons on the first orbital. We're going to talk a lot about this, but basically the innermost electron orbital can only hold 2 electrons. So it's full with just 2 electrons. All the others are 8. And there's some exceptions as well we'll talk about. Basically, 8 electrons is magic for stability reasons. Okay, so that's why the ionic bond forms. Now, water is covalent because the H is not a metal. It is an anion. Oxygen is an anion. So this is -1 if it was an anion. That's -2 if it was an anion. Okay, so there's no electron transfer here. Let's look at the orbitals now. Okay, hydrogen is the easiest. It has 1 electron running around the first orbital. So the first orbital can hold 2 electrons. So the first orbital's magic number is not 8, it's 2. So hydrogen is not stable now because it doesn't have 2 in its inner orbital. It has 1. Okay, let's look at oxygen. How many electrons does oxygen have? Okay, neutral oxygen is going to have 8 total, right? 2 in the inner one. How many in the outer one? 2 plus what is 8? 6 electrons. Now, oxygen by itself is not stable. Why? It's not 8. Hydrogen is not stable by itself. Why? Because it's not 2. So what a covalent bond is, we can, instead of transferring electrons, we're going to share electrons to achieve 8. So what's going to happen is, let me rewrite the 6. It's different here. So what's going to happen is oxygen is going to share the hydrogen's electron. So collectively, we have 1, 2, 3, 4, 5, 6, 7, 8 collectively. The word covalent means co means share, valence referring to the valence orbital. So covalent molecule doesn't transfer electrons, it shares electrons. Okay, good.
So when you add oxygen gas and hydrogen gas, what do you need
Or be a Saturn rocket. That's the fuel they use.
Yeah, right.
Liquid oxygen, yeah. And it gives off a whole bunch of heat as well. So hydrogen gas, when it breaks apart with oxygen gas, is very, very stable water. Water is really stable compared to the separate gaseous molecules. And we're talking about, you've all seen the Saturn rocket take off, right? That's creating water. Something called liquid oxygen locks liquid hydrogen. Excuse me.
The cloud, the trail that is leaving behind is condensed water, vapor.
The first stages are solid. They're not liquid. So all the smoke you see is from the solid repellent reaction. When those fall off, then it goes to liquid. And most rockets are multi-stage. And sometimes they're the same fuel for each stage. Sometimes they're different. Like the shuttle, it's the first one's dry, kick them off, go get them in the ocean. And then the liquid one kicks in. And they also are gimbaled. So they can guide it by moving the gimbaled rockets around on the bottom. It's pretty wild.
Yeah, I
fact-
was looking at how they were trying to design a nuclear rocket. for, back in the 70s. They designed a nuclear rocket.
There is a company in Sacramento called Aerojet. Has anyone heard of that?
Oh, yeah, it's here. I forgot. It was here.
That's right. And my father-in-law was a test engineer for Aerojet. It's called Rocketdyne now. And his job was, get this, he was being paid to push an engine out till it failed. And when a rocket engine fails, it goes kaboom. That was his job. You got to push, push, push. So he's just testing the limits of the engines. So you get to explode stuff all day long, and not just explosion, a big explosion. It's pretty wild. Okay, so anyway, this is a covalent bond. We're sharing electrons. Now, the issue with covalent bonds is, question is this an equal sharing or an unequal sharing? Most of the time, it's unequal sharing. It's still shared, but it's not equal. What I mean by that is oxygen has a higher electronegativity than hydrogen. Remember, electronegativity is the tendency for one atom to attract another atom's electron. So oxygen here, being more electronegative than hydrogen, will pull the hydrogen's atom sort of this way. So this is called a polar covalent bond.
So in the present time, though, the hydrogen, each hydrogen will always have one electron while the oxygen but there's whatever.
Yeah, they're just taking advantage of getting to the octet. So you can get the octet two ways, transfer or share. Both wanting to get that octet, except for the inner one, which only has two. Again, the name of the game is stability. Can I combine and be more stable? Yes. Okay, so there's a polar covalent. That's when the electronegativity of one molecule versus the other is not equal. We have unsharing. Yeah. Yeah, we're going to eventually get to you're gonna look at an electronegativity table and you're gonna go delta En, if it's 0.5 or greater, will form a bond. And then the closer they are together, it's more of a balanced. The further those numbers get, it becomes more and more polar, up to like 5. Up to 5. No, yeah, just fourth grade math.
Okay.
4 minus 2 is second grade math, probably. Of course, they're teaching our elementary schools and middle schools are using math that is really different these days. You know, the core and all this stuff. It is, I don't know what to say. You know, you ask a student, a sixth grader, multiply 14 times 12. They don't go 4 times 12, 1 time, you know, and then move it over. They don't do it that way anymore. It's like 5 steps instead of 1. Okay, so a polar covalent bond then is sharing, but unequally. Okay, so the driving force is achieving that outermost valence orbital to be basically full. The innermost one is full at 2. The outermost ones from helium on are 8. So they call it the octet rule. The problem with the octet rule is there's a lot of exceptions to it. So what I like to say is it's called a full shell. So the valence orbital, I'm going to call a shell. When that shell is maximized, it's stable. So in the case of the first orbital out, the shell can only hold 2. So when there's 2 electrons in there, it's very stable. The next orbital out can hold 8 in the shell. So it's maxed out, so it's stable. Yeah.
How many electrons are in like the outer shells for like specific groups, like nitrogen group? Like hydrogen, for example, I guess like 1 electron. Memorize pretty well, but like once you go to phosphorus or other elements like that, how do you memorize how many shells?
We're gonna go big time detail into that. So for right now, though, we're just keep it real simple. And basically, when you get to shell 3 or period 3, things start getting interesting. When you get to the transition metals, the ones in the middle, are all over the place. So, and I'm going to give you some. One student of mine 12 years ago invented this little trick. I've been using it ever since. Her name is Chris, and she's 3 kids, single mom, worked, got an A in my class. I don't understand when she slept, but anyway. Yeah, there's a trick for all that. So that's a really good question. Yeah, because it varies a lot. There are different, you know, there's S orbitals, P orbitals, D orbitals, and F orbitals. And they all hold different numbers of electrons to achieve the full shell. Okay, so now you know the reason for a bond, stability. So if a thing can become more stable by forming a bond with something else, it will happen. Now, there's a bunch of details to that, you know, things like entropy, randomness, and a bunch of other stuff. But basically, we're looking for one word: stability. And if you think in your head, if in doubt why this happens, just say it's more stable. And that's a really reasonable answer frequently, because the universe likes stability. Just think about your last relationship. Wouldn't it be nice if things went really well and it's nice and stable, right? You don't want things to be blowing up all the time. And trust me, I've been through my fair share of seeking stability in a relationship. But the same thing, it just wants to become more stable. Yeah.
I was going to say, like when a letter falls, it's more stable on the ground than it was standing up.
That's right. If I drop this, which is more stable, here, there? That means from energy perspective, we went from potential energy to lower potential energy. But when we lose the potential energy, it has to be converted to something, kinetic energy. So in the case of a molecule, that kinetic energy is the movement of molecules. And the metric for measuring the movement of molecules is called temperature. So when the kinetic energy of a molecule increases, its kinetic energy increases, hence its temperature increases. But with something that's macro, like this pointer here, it's just converted to plain kinetic energy, which can do work. Now, as far as molecules are concerned, potential energy is tied up in bonds. Okay. So let me, so we've talked a lot about ionic bonds. Let me just quickly. So covalent compounds are not ionic. Hence, there's no transfer of electrons. It's only sharing of electrons. So there's no way to balance a binary covalent compound because there's no charges to deal with. So we have to do it another way. And that other way is just using the mono, di, tri, etc. So let's look at water again. I've already mentioned that water is a covalent compound. That means you have to use the covalent naming convention. Both these, both ionic and covalent, are in two parts. So the first part is name the first element via the periodic table. So what is H? What's the name of H? This is a tough one now. Hydrogen, okay. And the second one is an ide. Okay, so oxygen as an ide. If you look on the ion chart, oxygen is what? Look on the top right. What is it called? It's a non-metal. Well, what's its specific name? On this guy here, on the ion chart. Yeah, oxide. So this is hydrogen oxide. However, it's not balanced because we don't know the numbers. So this would be di, because there are two, and monoxide. And normally when we have mono and another vowel, we usually drop the mono's last O. So instead of monoxide, it's monoxide. So dihydrogen monoxide, AKA water. Yes, there's also an SDS first aid on dihydrogen monoxide. Did you know this stuff is ubiquitous? It's all over the place. Bad stuff. Kills people all the time. You get too much of it, die. You don't get enough of it, you die. Yet it's all over the place. It's cheap too. You know, you can kind of make a case out of a lot of things. Okay, so that's the hard part on covalent naming. It's pretty straightforward. But you need to identify whether it's ionic or covalent before you can name it. Okay, so that's what I wanted to cover for today's dry lab. And you're just going to be practicing a whole bunch. Now, again, I want you to look at the exercise, and I would suggest jumping around and making sure you can do all examples. Maybe do 3 from each little grouping. Here's the formula, name it. Here's the name, write the formula, back and forth. And then when you think you know it, you're done. But I would recommend just every day, do some of these. I want you to get really comfortable with this. Okay, so from now till when you're done with the worksheet, wherever you feel like you want to finish is fine. If you're done now, The exam is going to be heavy on stoichiometry. We haven't touched upon that yet. Heavy on stoichiometry. And then there's definitely going to be naming, definitely going to be dimension analysis. There. So how's your grandma? Better?
Oh, yeah, thank you.
Okay, so any questions about, yeah.
2 questions. Is there any place?
Huh?
Do we have to turn this into any place, or is it just for our own use?
No, 'cause I consider a worksheet. I'm going to give you the answers. So there's no point in, because everyone will get 100 on it if I give you the answers.
Okay.
So the purpose of the worksheet is just so you understand the material better, so you do well on the test.
Okay, and is there a study guide for this now?
Not, I haven't put one out yet now, but
Okay.
if you look at, send me an email to remind me, I'll tell you what to study.
Okay, cool. Thank you.
Basically, though, it's going to be stoichiometry, which we haven't covered yet, nomenclature, dimensional analysis, a little bit about bonding.
So you said that Charlie's on campus? right now?
Which one?
Oh, yeah, talk about it.
Yeah, I think it's in, well, for sure it's in files.